Hello, we are still on the solution or methods of solution for first order differential equation. So the third method that we will be covering for this day is the non-exact differential equation. So at the end of this video presentation, so the viewer should be able to identify or classify whether a first order differential equation is non-exact or not. And it also follows that once you were able to identify that it is a non-exact equation, so the student should be able to determine the general or the particular solution of the first order differential equation using the method for non-exact differential equations. So how do we differentiate non-exact differential equation from other methods for first order differential equation? So a differential equation in the form of an m function of x and y dx plus an n function of x and y dy would be equal to 0 is said to be non-exact if the partial derivative of the m function of x and y with respect to y is not equal to the partial derivative of the n function of x and y with respect to x. So as long as the partial derivatives of those two functions are not equal, so then that is classified as a non-exact differential equation. And in non-exact differential equation, so the idea is that we are going to determine an integrating factor so that would make a non-exact differential equation into exact. An integrating factor will be multiplied with the original differential equation. And then once it was multiplied, if we're going to test its exactness, it becomes an exact differential equation. So there are different cases in determining the integrating factor of a non-exact differential equation. So the first case is if we are going to find the difference on the partial derivative of the m function with respect to y to that of the n function with respect to x, and then we will be dividing it with the n function, so it should yield a function of x alone. So if it yielded into a function of x alone, then that is classified as a case 1. So the integrating factor can then be computed to be equal to e raised to the integral of f of x dx. On the other hand, if the difference of the two function and then divide it with an m function and then it yielded to a function of y alone, so therefore that is classified as case 2. So in that case, to determine the integrating factor, so we will be computing it using the e raised to negative the integral of g of y dy. So that is for the case 2. And lastly, so for our case 3, so case 3 is if y multiplied with an m function of x and y plus x multiplied it with an n function of x and y would be equal to 0. So therefore, we can right away determine the integrating factor to be equal to 1 over x multiply it with the m function, so minus y multiply it with n function. So that is for our case 3. There's no need to integrate. So as long as given m function is multiplied it with y and an n function of x and y is multiplied with x, so that would be classified as case 3. And the integrating factor would be straightforward 1 over x multiplied with an m function minus y multiplied it with the n functions. So now let's proceed with the methods or the process in solving a non-exact differential equation. So you would notice here that the method of non-exact differential equation is similar with exact equation. So the first step is still the test for exactness. So we are to determine whether a given differential equation is exact or not. and that is done through the partial derivative of the m function of x and y with respect to y, and it should not be equal to the partial derivative of function of n of x and y with respect to x. So once you were able to identify that it is a non-exact differential equation, so we will be finding the integrating factor. So we are going to identify, so what case will it fall into? So whether that is a case 1, so a case 1 would be everything is a function of x. For the case 2, the integrating factor is a function of y alone. And for the case 3, so as long as the m function is multiplied with y and the n function is multiplied with x, so the integrating factor can be taken. So using the 1 over x multiplied with m minus y multiplied it with n. So that is on how to find the integrating factor. The next step is, so once integrating factor was determined, so we will be multiplying. So we will be multiplying the original differential equation by the integrating factor. And from there, so we can now check so whether the non-exact becomes exact. And that is, so once we multiply the integrating factor and then we're going to test its exactness, so this time around, it should become an exact differential equation. So once we are already sure that the integrating factor that we computed and multiplied with the differential equation is correct, and then we will proceed with the solution or finding the general solution of the first order differential equation, so following similar method that we had in exact equation. So for me, usually what I am doing, so since the non-exact has a longer solution already, so instead of following the methods for non-exact equation, so the methods of grouping would be a lot simpler and the process would be shorter. So without further ado, so let's try to proceed with our first example. So for our first example, so we have 3y squared plus 4x dx, and then plus 3xy dy, and that is equal to 0. So our first step is, again, to determine the exactness, or whether it is exact or not. So our m here is 3y squared plus 4x, and our n function would be equal to 3 multiplied with x times y. So finding the partial derivative of m, so with respect to y, so giving us 6y, and 4x will be 0. On the other hand, the partial derivative of n, so with respect to x, so that will be equivalent to 3y. So in here, so we can see that 6y is definitely not equal to 3y. So therefore, this is a non-exact differential equation. So for non-exact differential equation, our next step is to determine the integrating factor. So to determine that, so we will be classifying so whether the given differential equation falls on the 3 different cases. So let's try to take a look at our partial derivatives. So typically, definitely it's not a case 3, although n here is multiplied with x, but as you can see, the function of m here is not multiplied with y, so therefore it is not case 3. So it only follows it's either a case 1 or a case 2. So case 1 and case 2 would have the same numerator, so which is the difference between the partial derivative of m with respect to y and the partial derivative of n with respect to x. So the thing here is, what are we going to divide it? Are we going to divide it with m, or are we going to divide it with n? And from here, so if I'm going to substitute it, so I'll get 6y minus 3y, and that would be equal to 3y. So in here, there are two choices. So it's either I'm going to divide with 3y squared plus 4x, or I'm going to divide it with 3xy. So for case 1, it appears that it is logical that I'm going to divide it with n. So since my answer here is just 3y, so definitely something would cancel out if I'm going to divide it with n. So that would give us a 3xy. Okay, and then I'll have a 3xy there. So 3y would cancel out, so leaving me a 1 over x, and that is a function of x. So therefore, this given example is a case 1 non-exact differential equation. So since our f of x is equivalent to 1 over x, so our integrating factor, or that is the mu of x, so that is equal to e raised to the integral of f of x dx. And this would be equal to e raised to the integral of 1 over x dx. And this is e, the integral of dx over x is ln x. And therefore, our integrating factor then, so simplifying using the laws of logarithm or rules of logarithm, so our integrating factor then is equivalent to x. So our next step now would be, we are going to multiply our integrating factor to our original differential equation. So our original differential equation is 3y squared plus 4x dx plus 3xy dy is equal to 0. And our integrating factor here is equal to x. So I'm going to multiply everything by x. So giving us a 3xy squared plus 4x squared, then multiply it with dx, then plus 3x squared y, and that is dy is equals to 0. So now that we multiplied the integrating factor, so this time around, so this should be an exact equation. So to check that out, so we will be finding the first derivative again, or the partial derivative, 3xy squared plus 4x squared. And the partial derivative of m, so with respect to y, so would be equal to, so 3x is constant, derivative of y squared is 2y, so giving us a 6x multiplied it with y. So for x squared is constant, so making it 0. And while our n then, so would be equal to 3x squared y. So the partial derivative of n with respect to x would be 3 times 2 would be 6, x times 1. So as you can see, this time, the two are equal. So making our equation now to be exact. And as I've mentioned before, the easier method would be the method of grouping. So I'll be dealing with my exact equation. So the first one is the differential is dx. So they're making x to be the variable 1. So I'll move out 3y squared, and then the integral of x dx. Then plus 4, the integral of x squared dx. then plus. So the next one, our differential is dy, so making y as the variable. So 3x squared, the integral of y dy, and that is equal to 0. So integrating the whole equation, so will give us 3y squared, and then x would be x squared all over 2. So plus 4 x squared will become x cubed over 3, then plus 3x squared, and then y would become y squared all over 2, and that would be equal to C. So simplifying, so 3 over 2 x squared y squared plus 4 over 3 x cubed plus 3 halves of x squared y squared is equal to C. And again, as you can see, 3 over 2 x squared and y squared is the same as the 3 over 2 x squared y squared of the other term. So making them a group. And in this case, so if I would want to remove the denominator, so I'll be multiplying everything by 6. So giving me 6 divides 2 would be 3 times 3, I'll have a 9 x squared y squared, and then plus 6 divides 3 is 2 times 4, I'll have 8 x cubed, and that would be equal to C. So giving me the general solution for our differential equation, so to be 9x squared y squared, so plus 8x cubed, and that is equal to C. So that's it for our first example. So let's have another one. So for our second example, so we have y to the fourth plus 2y dx plus xy cubed plus 2y to the fourth minus 4x dy, and that is equal to 0. Again, our first step would be to test the exactness of the given equation. So m here is y to the fourth plus 2y. Its partial derivative, so with respect to y, would be 4y cubed plus 2. And n here is xy cubed plus 2y to the fourth minus 4x. So its partial derivative, so with respect to x, would be, so x is 1, so I'll have y cubed, 2y to the fourth is constant, so that is 0. So minus 4. So giving me y cubed minus 4. So again, this is a non-exact equation. So let's try to find the difference between the two partial derivative. So with respect to x, and that is equal to 4y squared plus 2. Then this is minus, so negative y cubed, and negative, so giving me plus 4. So negative, so plus 4. So finally, so that would be 4y, sorry, this is 4y cubed minus y cubed. So I'll have 3y cubed, and then 2 plus 4, I'll have plus 6. Okay? So what are we going to divide? Are we going to divide it with m, or are we going to divide it with n? So usually n is too complicated, so there are three terms. I only have two terms here. So I guess the more logical one, if I'm going to divide it with m, so in this case, so that would be y to the fourth plus 2y, or y to the fourth plus 2y. So in determining the case, so as you can see, so everything involves y. So it appears that our differential equation so falls under our case 2, so g of y. However, we can still simplify our given function of y. So g of y here is equal to, I can factor out 3 on the numerator. So 3, and that would be y cubed. And then plus 6 divides 3, I'll have 2. The same way, on the denominator is factorable by y. So y to the fourth divided with y is y cubed. So 2y divided with y. So that is 2. So we can now cancel out y cubed plus 2 and y cubed plus 2. So giving us the g of y, so to be equivalent to 3 over y, so which is a function of y alone. And therefore, so we can now get the integrating factor. So our integrating factor then, so would be equal to mu of y. And our formula would be e raised to negative the integral of g of y dy. And that is e raised to negative the integral of 3 of y dy. So which makes it e raised to negative 3 ln y. And this would be equal to, this in the same way, so e raised to ln y raised to negative 3, or making it y raised to negative 3, or our mu of y then would be equal to 1 over y cubed. So let's try to check now so whether our integrating factor is correct or not. So by multiplying it with our original differential equation, so which is y to the fourth plus 2y dx plus xy cubed plus 2y to the fourth minus 4x dy, and is equal to 0. So multiply everything by 1 over y cubed. So from here, so y to the fourth divided with y cubed, so leaving me a y. And then plus 2 y over y cubed, so 1 minus 3, so giving me 2y raised to negative 2, and I multiplied it with dx. Then plus, so y cubed and y cubed would cancel out, so leaving us an x, and then plus 2 y to the fourth divided with y cubed, so giving us a y, and minus 4x, and then y raised to negative 3 dy, and that is equal to 0. So let's try to verify if it should be exact this time around. So our m is equal to y plus 2y negative 2. So the partial derivative, so with respect to y, is equal to y is 1, and then minus 2 times 2 is 4, y raised to negative 3. So on the other hand, so I'll have n, so which is equals to x plus 2y minus 4xy raised to negative 3. So the partial derivative of n, so with respect to x, so this time, so x is 1, so 2y would be 0. And then our partial derivative, so with respect to x, so we'll just have derivative of x is 1, so a negative 4, and then y raised to negative 3. So again, the two are equal, so making our differential equation this time around to be exact. And to answer this one, so again, I will be employing the methods of grouping. So I'll start with the exact equation, so the one that was multiplied with the integrating factor. So we'll start with the differential dx. Y would then be multiplied with the integral of dx, then plus 2y raised to negative 2, again the integral of dx, then plus this time we'll have dy, so x, the integral of dy, plus 2, the integral of y dy, and then minus 4x, the integral of y negative 3 dy is equals to 0. So integrating the transformed equation, so this will yield to xy, and then plus 2x y raised to negative 2, then plus x, integral of dy is y, and then plus, so 2 multiplied it with y squared all over 2, and minus 4x, and the integral of y negative 3, so will be y raised to negative 2 all over negative 2, and that is equal to c. So simplifying it further, so giving us xy plus 2xy raised to negative 2 plus xy, then 2 would cancel out, so yielding to y squared alone, so negative and negative, so that would be plus 2, then x y raised to negative 2 is equals to c. So xy will be grouped into 1, while 2x y negative 2, so will be grouped into 1 as well. So giving us xy, so plus 2x, so I want to make y negative 2, so be positive, so I'll bring it down, then plus y squared is equals to c. So removing y squared on our denominator, so giving us xy cubed plus 2x plus y to the fourth is equal to c y squared. So that would give us our general solution. So to be x y cubed plus 2x plus y to the fourth is equals to cy squared. So that is for our second example. So we are done now with our first example, which is a case 1. Second example is a case 2. So let's proceed with the third example. So I think this would be a case 3. Okay, looking at the differential equation without doing the computation. So if this is a non-exact equation, so there is already a resemblance of a case 3 because we have y there, multiplied it with an m function, and then an x multiplied with the n function. So making it a case 3. But let's try to check. So if it is non-exact or not. So m then, so I'm going to distribute it right away. So this would be y minus xy squared. And then our n would be equal to x. So the partial derivative of m with respect to y is equal to 1 minus 2xy. And then our n with respect to x, so that is equivalent to 1. So if I'm going to subtract the 2, so 1 would cancel out, so leaving me negative 2xy. So the simpler to divide here would be the n. So dividing negative 2xy with x, so leaving me a negative 2y. But for case 1, so once we divided it with the n function, so the resulting function should be a function of x alone. But in this case, so it's a function of y alone, so making it not a case 1. So definitely if I'm going to divide it with y, so it would be difficult to separate x and y. So it's not case 2 as well. So leaving us only the third case. So we're in on our third case. So it is very direct that our integrating factor, mu of xy, so that is equal to 1 over x raised to m minus multiplied it with n. And that is 1 over x, our m is y multiplied with 1 minus xy, and minus n here is x, so minus xy. So distributing the xy, so giving us xy minus x squared y squared minus xy. So leaving us for our integrating factor xy to be equivalent to negative 1 over x squared y squared. So that is our integrating factor. So let us now multiply that one, so with our original equation, and that is y multiplied with 1 minus xy dx, so plus x dy, that is equal to 0. So multiplying everything by negative 1 over x squared y squared. So multiplying that one, so will give us a negative y times 1 minus xy all over x squared y squared, and that is multiplied with dx, and then we'll have minus x over x squared y squared dy, and that is equal to 0. So simplifying this one, so giving us on our first term, so we'll have negative 1 over x squared y, and then plus xy, okay, so y squared, so we'll just have, so y squared would cancel out, y squared and y squared, so x and x squared, so leaving us 1 over x. Then multiplied it with dx. And then we'll have minus 1 over x y squared dy, and that is equal to 0. So let us try to check now so whether this is exact or not. Hopefully I'm doing right. So m would be equal to, so I'll bring it up, so that would be negative x raised to negative 2 and y negative 1, so plus x raised to negative 1. So the partial derivative of m, so with respect to y, so I'll just be dealing with y raised to negative 1. So negative 1 will have positive, so x raised to negative 2, and then y negative 1 minus 1 will have negative 2. And then x negative 1 would be 0. So next we have our n, so which is equal to negative x raised to negative 1 and y raised to negative 2. So the partial derivative of n, so with respect to x then, so would be, so negative and negative, so I'll have positive x raised to negative 2 and then y raised to negative 2. So that's correct. So again, so making it to be exact. So our next way is to integrate using the methods of grouping. So let's start with our first term. So our differential is dx. So I could move out the negative y, right? So I could have negative 1 over y, and that is the multiplied it with the integral of x raised to negative 2 dx, and then plus the integral of dx over x, and then minus 1 over x, the integral of y raised to negative 2 dy, and that is equal to 0. So I'll have now negative 1 over y, so multiplied it with x, negative 2 plus 1 is negative 1 all over negative 1. Then plus, this would be an ln x, minus 1 over x, so I'll have y raised to negative 1 all over negative 1, and that is equal to c. So simplifying this further, so a negative and a negative would be positive, so that is 1 all over, I'll bring that down, so x multiplied with y plus ln x, and then negative and a negative, so I'll have plus 1 over x, so y negative 1 will bring it down, it's equal to c. So making 1 over xy and 1 over xy on the same group, so leaving us 1 over xy, so plus ln x is equal to c. So if you want to remove the natural logarithm, so ln x then would be equal to c, so minus 1 over xy, and taking the exponential function of both sides, so leaving us x to be equal to c, then e raised to negative 1 over xy. So leaving us with our general solution, so to be equivalent to x, and that is equal to c e raised to negative 1 over xy. So that is our third example. So let's proceed with another one. So for our fourth example, we have 3xy minus y squared dx plus x times x minus y dy. So let's check again. So for partial derivative of m right away, so let's try to answer it. So with respect to y, so we'll have 3x minus 2y. On the other hand, so the partial derivative of n, so with respect to x, so x times x is x squared, so I'll have 2x, and the negative xy, so I'll have a minus y. So therefore it is non-exact. So taking the difference of the two, so I'll have 3x minus 2y, then minus 2x plus y. So leaving us to have x minus y. And it is obvious that we could divide n there. So giving us x times x minus y. So canceling x minus y. So 1 over x. So leaving us a function of x alone. So therefore our integrating factor, so which belongs to case 1. So our mu of x then would be equal to e raised to 1 over x dx. Or that is e raised to ln x, or that is equal to x. So multiplying our original equation 3xy minus y squared dx plus x times x minus y dy is equals to 0. So multiply everything by x, so yielding to 3x squared y minus xy squared, multiplied it with dx, plus x squared times x, I will have x cubed, minus x squared y, multiplied it with dy, and that is equal to 0. So let's try to verify, so if it is exact this time. So the partial derivative of m, so with respect to y, so would be equal to 3x squared, then minus 2xy. And then the partial derivative of n with respect to x would be 3x squared minus 2xy. So making it exact. So employing the methods of grouping, so on our exact equation, so leaving us 3y multiplied with the integral of x squared dx and minus y squared, the integral of x dx, so plus x cubed, the integral of dy, minus x squared, the integral of y dy, and that is equal to 0. So 3y then would be multiplied with x cubed over 3 minus y squared, x squared all over 2, plus x cubed multiplied with y minus x squared multiplied it with y squared all over 2. That is equal to c. So simplifying this one, giving us x cubed y minus x squared y squared all over 2, then plus x cubed y minus x squared y squared all over 2 is equal to c. So leaving us x cubed y to be on the same group, and the negative x squared y squared all over 2 on the same group as well. So giving us x cubed y minus x squared y squared all over 2 is equal to c. So multiplying everything by 2, so leaving us the general solution to be 2x cubed y minus x squared y squared is equal to c for our general solution. And lastly, so let's have another example. So this time it involves a trigo function, so which is the cosine x dx plus 1y, or 1 plus 2 over y multiplied with sine x dy, and that is equal to 0. So right away, so the partial derivative of m, so with respect to y, so this is cosine x, so therefore that will be 0. The partial derivative of n, so with respect to x, is equal to, the entire of this is y, so sine x, so that will be 1 over 2y multiplied it with derivative of sine x to be cosine x. So making it definitely a non-exact equation. But taking the difference of 0, so minus 1 plus 2 over y cosine x. So obviously, so we can divide it. Actually, we can, if I am going to divide it with n, so it will be a function of x alone. Okay. But if I'm going to divide it with m, so similarly, it would be a function of y alone. So in this case, it's either a case 1 or a case 2. But in this case, so since we're solving it before, usually using case 1, so I'll do this one with the case 2. So I'm going to divide it with m, so which is the cosine x. So therefore, this should be a function of y alone, which is true. So cosine x, so leaving us a negative 1 plus 2 all over y. And for our integrating factor, so mu of y then would be equal to e raised to negative the integral of g of y. So our g of y is negative 1 plus 2 all over y dy. So e then would be the integral of 1 plus 2 over y dy. So which is equal to e, the integral of dy is y plus 2 ln y. So which is the same as e raised to y plus ln y squared, or the same as e raised to y times e raised to ln y squared. So giving us the integrating factor mu of y to be equivalent to y squared e raised to y. So let's multiply this one with our original equation. So cosine x dx plus 1 plus 2 all over y sine x dy, that is equal to 0. So multiply everything by y squared e raised to y. So this would give us y squared e raised to y cosine x dx plus 1 plus 2 all over y squared e raised to y sine x dy, that is equal to 0. So m here is equal to y squared e raised to y cosine x. So the partial derivative of m, so with respect to y, so will be, I'll have cosine x first, and then multiplied it with the derivative of y squared ey, so using the product rule. So we'll have e or y squared, then derivative of ey is ey, then plus ey, derivative of y squared would be 2y. So giving us y squared e raised to y cosine x plus 2y e raised to y cosine x. So for our n, so we'll be distributing, we'll have y squared e raised to y sine x, then plus 2. So y squared over y would be y, so e raised to y sine x. So the partial derivative of m, so with respect to x, so derivative of sine would be cosine, so this would just be simply y squared e raised to y cosine x. And similarly, so this would be 2y ey cosine x. So making the two equal, so therefore that would be exact. So let's proceed with the methods of grouping. So for our methods of grouping, on our first term, so we'll have y squared e raised to y, the integral of cosine x dx. And then for our second term, so that is dy. So I'll have sine x, so plus sine x, and then the integral of y squared e raised to y dy. And lastly, I'll have plus sine x as well. So this time I'll have 2 sine x, and then the integral of y ey dy, and that is equal to 0. Correct? So 2 sine x, so y ey dy is equals to 0. The other ones, I'll have sine x, then y squared ey dy. So in here, so cosine x dx could easily be integrated, but y squared ey, so we could use integration by parts, so similar with y ey, but the easier one would be the tabular method again. So y squared, and then the other one is ey. So for the other one, we have y, and then we have e raised to y. So derivative would be 2y, and then 2, and then we'll have 0. So the integral of ey is the same throughout, ey ey. So y would be 1, and derivative of 1 is 0. Then I'll have ey. Okay, the solution is a bit longer, so positive, negative, positive. Positive here, negative there. So giving us our solution then to be y squared e raised to y, integral of cosine x would be sine x, then plus sine x, so multiplied it with positive y squared ey minus 2y ey plus 2 ey, and then plus 2 sine x. So the integral of y ey would be y e raised to y minus ey, that is equal to c. So distributing, so y squared e raised to y sine x, so plus y squared e raised to y sine x minus 2y ey sine x plus 2 ey sine x, then plus 2 y ey sine x and minus 2 ey sine x is equal to c. So as you can see here, this is negative 2y ey sine x. The function is the same, or the variables as well as the numerical coefficient are the same, but one is positive, the other is negative. So therefore, those cannot be combined as one. So rather, they would cancel each other out. And similarly, we have 2 ey sine x and minus 2 ey sine x. So that would cancel it out. So only the y squared ey sine x, so that could be grouped into one. So giving us our general solution to be y squared e raised to y sine x, and that is equal to c. So for our final general solution. So again, that's everything for non-exact differential equation. Thank you.